Okay, hey guys. Um, so I know last week's homework was really hard. So I have the key here. You could search these answers up to find the solutions. But let's take like 1 or 2 minutes for that. If you need a break, go ahead. Oh yeah, by the way, about the difficulty of the problems I'm giving. Like most of these that I find are in the late 20s of AMC10 or 12. So it makes sense if you don't know how to do most of them. Hopefully you did learn how to like kind of get started. Okay, I hope that was enough time. All right, so this week we're doing a warm up first, going over altitudes from last time, and then we're doing 2D coordinate geometry and 3D geometry. So let's take 2 minutes for a warm up. I'll switch over to this. Okay, here's a diagram. And we know that all triangles have 3 altitudes. So first off, notice that this is a 3, 4, 5 right triangle. That means that 2 of the altitudes are the legs, so 20 and 15. And the smallest altitude always corresponds to the longest side length. You can see for yourself why that is. So I know that this altitude going to the longest length of 25 is going to be the shortest length. So to find that, I can find the area in 2 ways. First, by doing base times height over 2 with the legs, and that gives me 150. And the other way, I can do it by doing 25 times x over 2. And the area stays the same, so that should also be 150. And solving for x, I get x is 12. All right. So hopefully that was pretty quick. So we're starting with 2D coordinate geometry. Now it has a pretty bad reputation. Oh, first off, so starting next year, we won't be able to bring graph paper for the AMCs and AME. This year and the years before, we were able to bring graph paper, and that helps a lot. I'm not sure if they provide it, but I know that at least we won't be able to bring it ourselves. So make sure you bring a ruler and a compass if you're able to for the AME, because those will be really useful. Sometimes you can even guess the answer by drawing a good diagram. All right, so when do we use coordinate geometry? Typically when we're looking at like segment ratios, we want to use it if we can't use similar triangles or like mass points. If we're looking for distances, then yeah, like finding the distance between 2 points is going to be easy. If we have clean numbers, and by clean numbers, I also mean clean diagrams. So we don't want like random angles in our diagram. We want like right angles and all that. We want perpendicular and parallel lines because we can use slope to relate those. And we could use it if we're looking for like finding the area or the perimeter fast. So typically it's going to be very computationally heavy. You'll find that coordinate geometry problems often just digress into algebra problems, like with a lot of equations and a lot of variables. So use it if you're good at that. But I would recommend to first like find a synthetic solution. So a solution that doesn't require this. And then a general tip is to center the plane. Like once you put your diagram on the plane, make sure that it like fits, or make sure that it's a good position and a good rotation. So you want your lines, as many lines as possible, to like be on the be parallel to the axes. All right, so of course we're using the coordinate plane, the x and y directions, and points are represented using the x coordinate and the y coordinate. So one trick is like the midpoint of 2 points is going to be have the coordinates of the averages of the x coordinates and the y coordinates. All right. So our distance formula for finding the distance between 2 points comes from the Pythagorean theorem. So given points P and Q, this is our formula for finding the distance. And you can see this x2 minus x1 is like our A, y2 minus y1 is like our B. The slope between P and Q, given these same coordinates, is y2 minus y1 over x2 minus x1. And then when we're comparing two lines with looking at the slopes, then we can tell that they're parallel if their slopes are the same, and they're perpendicular if the slopes multiply to -1. Okay, and then one formula I'm introducing is the Shoelace formula. And this is a quick way to find the area of a shape given the coordinates. So the best way to show this is by actually like doing it out. So I brought this diagram over here. And in this example, we have 4 points, but we could have any number of points. And what I did here is I have an X column, a Y column, and I listed out all of my points so that their X coordinate is here and their Y coordinate is here. And notice that I repeated the first point and the last point at the top and at the bottom. So this is 1, 0. Ooh, actually, oh, this isn't. All right, this is a very bad example, and I will explain why in a second, or I'll explain why. It's because, all right, so I'll get rid of this. I'll just work it out from the beginning. We have 1, 0. This is 5, 3. This is negative 3, 4. And this is negative 2, 1. So we're given this. Now I'm going to make my table. And when I make this table, I have to make sure that all the points are in order. So I accidentally messed up earlier there. I wasn't paying attention. So I choose one of these points. I'm going to choose 1, 0 to be my first point. And then I just choose the direction to go in. So I'm going to choose this direction. So from now on, I have to go in this direction. And each time I visit a point, I write down that point. So I start at 1, 0, then I write down 5, 3. Then I go along this edge. I go to negative 3, 4. And then negative 2, 1. And finally, I write down my first point again. So that's 1, 0. All right, my next step is to use this table, and then if it helps you, draw lines between the opposite sides like that. So I take this, all of these lines that are going down like that, and I add those products. So I take 1 multiplied by 3, which is that. Add it to 5 multiplied by 4. Add it to negative 3 multiplied by 1. And then add it to negative 2 multiplied by 0. Okay, so that's my first term. My second term is doing the same thing, but with the ones going up like that. And I subtract the entire sum from the first sum. So it's 0 times 5 plus 3 times negative 3 plus 4 times negative 2 plus 1 times 1. All right, and finally, I take the absolute value of that and I multiply by 1/2 to get the area. So I could have made my table like this too. I could have started from 5, 3, went to 1, 0, then went to negative 2, 1, negative 3, 4, and then back to 5, 3. And I'll get the same answer. And that's due to the fact that there's an absolute value here. And all of these numbers are going to be the same regardless. Okay, so we'll be using this, and I'll do the process again and the problem. So actually, I'll go back to this. Our first problem is this one. Okay, I'm gonna draw in. Okay. So let me draw in those lines. Some lines. So these lines are where the points have to fall on. The line over here is x is 0. This is x is 1. Oh, sorry, these are y. Oops. So this is y is 0, y is 1, y is 4, and y is 5. So without loss of generality, gosh, okay. I'm gonna let one of the points be here because I know that I can just shift this square, excuse me, along this like these lines, however I like. So I'll just put one of my points here. Then I'll put another point over here, a third point here, my fourth point here. So it just takes a little like trial and error to see where the points are gonna be at. Okay. Now, notice that this triangle, so this black triangle over here, is the same as that triangle, the other black one. This one has a height of 1 and a length of, I don't know, so I'll just call the x. This one has a length that I don't know, but a height of 4. So I know that this has to be 1 and x has to be 4. And I know this was 4 because it lies on this line and that line. So 4 minus 0. So this is a 1, 4, and then something, right triangle. And now to find that length, I can just use the Pythagorean theorem. So it's root 17. And that means my square's area is 17. All right, I'll leave that up for a minute. Okay. Next one. Okay, I have point A at 6, 8. And the two y-intercepts of P and Q of two perpendicular lines intersect at A. So I have two lines that go through A that are perpendicular. I'll make a rough estimate. So I'm going to assume that that's A, that's P, and that's Q. And it says that the y-coordinates here have a sum of 0, basically meaning that this length is equal to that length. Okay, so I have the origin here, and I know that, let me call that O. I know that PO equals QO, and PAQ is a right angle. And actually, we've seen this diagram before. This triangle lies on a circle. So if I drew the circle with center O going through P and Q, then A would actually lie on it. And that's because this is a right angle. All right, so I drew a circle with this radius intersecting P and Q and center.O. And I know that it intersects A because PAQ, this angle, is a right angle. And now I know that OA is also a radius, right, because it lies on the circle. And this has length square root of 6 squared plus 8 squared. The distance between 6, 8 and 0, 0. And that's root 100 or 10. All right, so finally, I know that the radius is 10. So PO is 10, QO is 10. And I'm trying to find the area of APQ. I'll just do that by using the base times height formula. This is 20. And then the x coordinate of A is 6. So I know that I moved 6 units out to the right. So the area is 6 times 20 over 2, and that's 60. Okay, so I'll go through the process one more time because this was kind of tricky to see. I have P and Q down here, and they're equidistant from O, the origin, and A is at 6, 8. And since APQ is a right triangle, then I know that they all lie on a circle with center at O. So the distance between O and A is square root of 6 squared plus 8 squared, and that's 10. So that's the radius, which means that OP is also 10, and OQ is also 10. And then finally, to find the area, I have 20 as the whole diameter times the height, which is 6. And then divided by 2. All right. And then our last problem for 2D geometry is here. Okay, I'm gonna draw ABC. Okay, so this goes back to what we did, I think 2 weeks ago when we talked about medians. So I'll draw median AD and BE. AD, BE. And they intersect at F. So we're looking for AFB. I'll show 2 ways to do this. So the first way is knowing that AC is 2 and BC is 3. I'll first find the area of ABC. And that's 2 times 3 over 2, which is 3. And then let me draw in this last median. So I'll call that M. So CM is that last median. I'm not sure if you remember, but actually all of these areas, all of these little triangles, so A, E, F, so this one, that one, that one, that one, this one, they all have the same area. So if you knew that, it would be a lot easier because then each of those areas is 3 over 6, which is 1/2. And then since I'm looking for AFB, that's 2 of them. So 2 times 1/2, and my area is 1. So that's if you knew that little trick, if you knew the fact that all 6 areas were the same. But let's just assume that we didn't know that. We could use mass points to resolve for the fact that AF to FD is 2 to 1. So AF over here to FD is 2 to 1. And that was just another property of medians intersecting. But you could use mass points to find that out. All right, so if that's 2 to 1, now let me transfer everything onto a coordinate plane. So at this point, if I'm really stuck and I don't know how to do it anymore, I could let C be 0, 0. Let B be 3, 0. All right, I chose this to be the x-axis, and BC, that length is 3. And then I'll let A be 0, 2. Okay. And I'll try finding the coordinate of F, because once I find the coordinate of F, I can use the Shoelace theorem to find the area of AFB. I have A and B, but I don't have F. So to find F, let me find M first. And M is the midpoint of AB because it's CM is a median. So I'll take the average of 0 and 3. That's 3 halves. And I'll take the average of 2 and 0. That's 1. So the coordinate of M is 3 halves 1, which is halfway. And then to find the coordinate of F, like AF to FD, CF to FM is also 2 to 1. So let me redraw that line, CM. And this is 2/3 of the way from C to M, F. So C is 0, 0. M is 3 halves, 1. So how I would do this is find the x displacement, like how far, what the difference is for the x value. That's 3 halves. And then find the y distance. That's 1. And then since this length is 2/3 of cm, I can multiply all these values by 2/3. So this becomes 2/3 times 3 halves, which is 1. And then this length becomes 2/3 times 1, which is 2/3. So what does that mean? That means my coordinate of f is 1, 2/3, because I went 1 to the right of c, and then 2/3 up from that point. All right, so my coordinate of f is 1, 2/3. And finally, let me circle this. To find the area, I use the coordinates a, b, and f. So I'll use shoelace. A is 0, 2. B is 3, 0. F is 1, 2/3. And then I have to write A again, 0, 2. And I'll do shoelace. So multiply that. I get 0 times 0, which is 0, plus 3 times 2/3, that's 2, plus 1 times 2, that's 2. All right, I have that, and then subtract those 3 values. 2 times 3 is 6, 0 times 1 is 0, and then 2/3 times 0 is 0. And remember that this whole value is taken, is halves and absolute valued. So this is 1/2 times the absolute value of 4 minus 6, which is 1/2 times 2, which is 1. So 1's our final answer. But it would have been much faster to just do it the normal way. So I'll zoom out and then go back to that. Okay. So our next topic is 3D geometry. And this is like where geometry gets kind of hard. But the hardest part is just visualizing it. To help with that, like for this diagram specifically, I would draw a top view. So like this thing, and a side view. So let's say we're like solving for the height. We also want to draw the height in. But it just takes a lot of practice until you get like used to seeing these diagrams, and then you can like kind of see like you can kind of like see the steps being played out. Like how would you solve for the height, or how would you solve for the slant length? And the most useful formula is, of course, the Pythagorean theorem. For the 2D one, we have x squared plus y squared is d squared, or a squared plus b squared is c squared. We should know that. And the 3D one is basically the same thing, but in 3 dimensions. So with an x, y, and z all going in different planes. This is a weird diagram, but imagine that this bottom triangle, YZ, is on the table, and then x, y is like up here. You can still solve for d using this formula, but it's like the same thing as finding this bottom length and then using that and z to find, finding this bottom length using y and z, and then using x and that bottom length to find d. So it's the same thing, but there's a clean formula for it. Okay, so let's do some questions with that. All right, so already this is actually like really, really hard. I purposefully chose hard 3D problems. Well, first off, because there aren't many easy 3D problems, but also because this one shows you a technique that you can use. All right, so I have a hemisphere, which is half a sphere, on the base of a square pyramid of height 6. So my first step when I approach this problem is I read it through, know that it's 3D, and then I get an idea of like the symmetries of the problem. So this square pyramid looks like that. Right. And this hemisphere is going to have its base over here and then touching those side lengths. So already like this diagram is very, very confusing to look at. So you have to read the question and then look at what it's saying. So it says that this hemisphere is tangent to the other 4 faces of the pyramid. So now I'll look at a 2D view of this diagram, and I'll look at it where this hemisphere touches the pyramid. So imagine that I took this diagram and then I'm looking at it straight forward. And what do I know from this? Well, I know that this height is 6. and the radius of this hemisphere is 2. Okay. If you don't see where I got this diagram from, try imagining if I just cut the shape directly in the middle, and then now I'm looking at it from the front. This should make sense because the 6 goes straight down perfectly onto this point because it's halfway, because I cut it perfectly in the middle. And then it's tangent here because it's always tangent. It's going to be symmetrical, so it's going to be touching the square pyramid at the halfway points. So the more I explain this, like the more confusing it gets. But if you see this diagram, that's great because now we can solve for what this edge length is supposed to be. So this whole length is the whole base is what we're looking for. I'm just going to call half of this x. Okay. And I know that this can be found by using 6 squared plus x squared. That's the Pythagorean theorem because I have 6 and x. And I can use that trick from the warm-up I did. I can find the area using 2 methods, or in 2 different ways. First, by 6 times x over 2. So that's, I'm finding the area of this left triangle, by the way. And that's by using base times height over 2. And I can also solve it by using this hypotenuse as the base. Times 2 over 2. So I'll get rid of that. I'll cancel out a 2. So now I have 3x equals square root of 36 plus x squared. All right, and I can solve this now. Squaring both sides, I get 9x squared equals 36 plus x squared. Then 8x squared equals 36. X squared equals 18 over 4. And finally, x equals 3 root 2 over 2. Okay, so I'll go back through the process one more time. So I wrote the problem, make sure that I knew like what the diagram looked like in my head. And then if it helps, you can draw out this little 3D shape, but it doesn't really tell you much, right? Then you have to look at like, well, what 2D view is going to help me the most? And in this case, this 2D view, looking at it straight ahead, is going to be the most useful because here, this is where the hemisphere intersect or is tangent to the side faces. And then taking this view, I can now find the value of x and then solve for the whole base, right? So this was very hard. The hardest part is visualizing and determining which face or which 2D view is the most useful. All right, so I have another one. And while you're reading this, notice that this question is like very different from the previous question. So for 3D problems, like there's so many things that you could be tested over. And I purposefully chose problems that are very different. Oh, sorry. I just realized I solved for x is 3 root 2 over 2. The side length of the base is 3 root 2 because it's twice of that. Thank you for pointing that out. Okay, let me draw this cube. And the sphere is inscribed inside of it. Now, first, I'll use the fact that the surface area is 24 to find the side length of the big cube. I'm talking about the outer cube. So the surface area formula is 6 times s squared, because 6 sides, and then each face has an area of s squared, and that's 24. So my s value is 2. Each side is 2. And it says that a sphere is inscribed inside of it. My sphere rests inside of it like that. And again, because of symmetry, I know that the sphere touches the top, the cube at the top in the very middle, and it also touches the bottom in the very middle. So if I connect those 2 points, I should get the diameter of the sphere. And that's length 2, right? This is the same as that. Which means that since my diameter is 2, my radius for the sphere is half of that, or 1. All right, and then now I'll draw another picture, but this time I have my cube inscribed inside of the circle. Oh, sorry, inside of the sphere. But as I draw it, I'll realize that like the best way to do this isn't to draw it out, but like to think about, well, how do I solve for the side length of a cube? It's going to be difficult to like relate directly the side length of the cube to the radius, but I can relate a space diagonal to it. A space diagonal is the line, the diagonal connecting 2 opposite points of a cube. So it's directly opposite from each other. And I know that if I inscribe this cube, if I put this cube inside of the circle, then it's going to be, then these 2 points are going to be opposite of each other and touching the sphere. I didn't directly prove it, but I can assume that this is the case because it should be true for all of the other pairs too. So what is this length? To find the length of this space diagonal, I can use the Pythagorean theorem for 3D shapes. So I'll let this side length of the cube be x. Then this distance d equals square root of x squared plus x squared plus x squared, which is root 3x squared, which is root 3 times x. And what is this equal to? Well, it's equal to the longest distance inside a sphere, right? I can imagine that I put my cube inside like that. So the longest distance inside a sphere is the diameter, which has length 2, which we found earlier. And solving for x, we get 2 over root 3 is the side length of the inner cube. All right, so finally, to find the surface area, let me find the surface area, or the area of one of the sides. So x squared equals 4 over 3. And 4 over 3 is multiplied by 6 to get the total surface area. So my answer is 8. All right, so I had 2 more problems planned out, but this took more time because these problems are, again, very challenging. That's all for this week. So we're good for today, and we'll have the keys posted within this week. I'm not too sure when we're to post them, honestly. Again, thanks for coming. Isabella, is there anything else?
Thank you guys so much for coming this week, and see you soon. Have a great week, but guys, bye.
Bye.